Welcome to the sixth part in our time series course. Today, we will start looking at co-integration analysis. We will start with a motivating example and a formal definition of what co-integration is. Then we will look into several co-integration representations. And in the last two parts of this lecture, we will set up a co-integration test and we will estimate the co-integration relation. Now let us start with a brief overview of what we have been doing so far. During the first lecture weeks, we worked with stationary time series. We saw how to model single stationary time series through ARMA models, and also how we can jointly model multiple time series in the VAR framework. We then extended our toolkit of asymptotic analysis to time series, since we saw how to extend the law of large numbers and central limit theorem to dependent processes. In a second large chunk of the course, we looked at non-stationary time series. We saw how to set up unit root tests to formally test if a series is stationary or not. And these non-stationary asymptotics required us to rely on Brownian motions and the functional central limit theorem. We also saw at the end of last week that we needed to be careful with non-stationary time series, since spurious regressions can lead to nonsense relations. What will we now do in this last part of the course? Well, despite the fact that we need to be careful with spurious regressions, we can still detect meaningful relations between non-stationary time series. And that is what co-integration analysis is about. So two non-stationary time series are co-integrated if there exists a long-run equilibrium relation between the time series. And we will formally define this co-integration concept, and we will see that the unit root behavior of linear combinations of our series will be crucial here. We will see that if a linear combination of our series is stationary, well, then our series are co-integrated, and this linear combination describes how our time series move together in the long run. We will also set up a test for co-integration, and we will estimate the co-integration relation in a single equations framework. Next week, we will then look at co-integration in a multivariate framework. Now let us start with some graphical intuition for co-integrated series. And on this slide, I have plotted several non-stationary time series. On the left, I have two series that have a unit root and that are unrelated. So this over here is the spurious regression framework from last week. On the right-hand side, I have again two series that each have a unit root, but this time they are moving together. So we say that these series over here are co-integrated, since they move together in the long run. So these two panels are quite different situations, and we would like to be able to distinguish these cases in practice. As we will formally see later on today, a crucial difference between both situations concerns the unit root behavior of a linear combination of our series. And on this slide, I've plotted here the difference between both time series, which is indeed a linear combination of our two original time series. Now, what do we see? Well, on the left, this difference series is still clearly non-stationary. Whereas in the right panel, this difference series looks much more stable. The series, this guy over here, is indeed stationary. So despite the fact that each series has a unit root, This linear combination removes the unit root behavior in my original series and it returns a new stationary time series. And it is exactly this long-run equilibrium relation between my series that ties them together in the long run and makes them move together. Now, let us look at some formal definitions. First, let us define the concept of an integrated of order D process, denoted like this here on the slide for integrated of order D. So a time series is called integrated of order D if I need to apply the difference operator D times in order to get a stationary time series. So a series that is integrated of order 0, so D equal to 0, means that it is already stationary on its own. Indeed, you need to apply the difference operator 0 times in order to get a stationary time series. It's already stationary. On the other hand, for a time series that is integrated of order 1, for instance, you need to apply the difference operator 1 time in order to get a stationary series. In practice, we do not know what D, the order of integration, is, of course, but a couple of lectures ago, we introduced the Pentula principle to determine a series order of integration. Now, in the discussion of co-integration today and next week, we will only look at series that are integrated of order 1 and investigate whether they are co-integrated or not. Now, how do we set up our definition of co-integration? Well, let's say that we have an n-dimensional vector process yt that is integrated of order 1, so non-stationary. Well, then the series are co-integrated if there exists a linear combination among my series, as given over here by a prime yt, that yields a stationary time series, so that is integrated of order 0. If this is the case, well, then I say that my series are co-integrated, and this vector A over here collects the coefficients of our series in this linear combination, in this co-integration relation. A very important remark to make is that the co-integrating vector is not unique. If A is a co-integrating vector, then any rescaled version by a non-zero constant lambda also gives you another co-integration relation. So while the co-integrating vector is not unique, what is unique is the co-integration space. So what is this co-integration space? Well, first of all, note that we can have possibly several long-run relations between our series. Let's say that we have S of them, and we have S corresponding co-integrating vectors, A1 to AS, that are all linearly independent. Then S is said to be the co-integrating rank. So it indicates how many co-integration relations we have. And the space that is spanned by these co-integrating vectors is unique and is called the co-integrating space. Now that we are armed with these formal definitions, natural questions are, how can we determine whether our series are co-integrated? And if they are, how can we determine how many co-integration relations there are? And how can we find and how can we estimate these co-integrating vectors? Well, we will dive into all of these questions today, and we start by inspecting the co-integrating implications for the vector moving average representation. So start from Walt's representation of the series in differences. Remember, the series in differences is stationary since we work with I1 series. Now, since this difference is stationary, I can write it as an infinite sum of past error terms, as given by this infinite order vector moving average representation. And if I introduce here my lag operator, I can compactly write down this infinite sum through my lag polynomial psi L here. So I recognize here the form of a linear process. And by now, you should know that we can conveniently analyze linear processes with our Beveridge-Nelson decomposition. If we apply this Beveridge-Nelson decomposition to our lag polynomial and insert this back into our first equation, we get this expression over here. Namely, that the series indifferences, this guy over here, can be rewritten as psi 1 times my error term, and then the difference of a new error process. Note that I have changed the time index from t to s, which I can do, of course, since the model equation holds at any time point. And the reason for this change in index will become clear on the next slide. So on this next slide, I recopied the expression that I obtained here in the last step of my previous slide. And what I will do next is take the sum at both sides over time points s equal to 1 up until small t. So the sum of this difference, and at the right-hand side, I also take this difference. What happens to the left-hand side? Well, I get the sum of all these differences, where, again, like we already saw a couple of times in the lecture videos from the previous weeks, we can recognize a telescopic sum, since only the last time point t and the initial one at point 0 will remain, these terms over here already. Okay, what do I have on the right-hand side? Well, I have my partial sum of the error terms. And for this difference, I also recognize the telescopic sum, such that only the last and the initial time point remain. Now, let us suppose that we have h co-integrating vectors, where h is smaller than n, the number of original series we have. The reason why we can maximally have n-1 co-integration relations will become clear later on in the videos. But so for now, suppose that we have h co-integrating vectors collected here in these A vectors. And let us gather them all in this matrix A prime. So each row in A prime contains a co-integrating vector. Note that A prime is of dimension h times n. And let us now pre-multiply both the left-hand side and the right-hand side from the box expression of the previous slide by this A prime matrix. What do we get then? Well, on the left-hand side, I have A prime times yt, which is nothing more than the h linear combinations of my original series according to the co-integrating vectors. So on the left-hand side, I have my co-integration relations. What do I have on the right-hand side? Well, on the right-hand side, I have to also pre-multiply with A prime, of course. And I know that since on the left-hand side, I have my co-integration relations, I know that these must be stationary in order to have co-integration. So if the left-hand side must be stationary, then the right-hand side must be stationary as well. Now, if we have a closer look at the right-hand side, what is the problematic part that may still contain a unit root? Well, you should recognize here a partial sum of the errors popping up still, which indeed still contains a unit root. So in order for yt to be co-integrated with the co-integrating vectors collected in the rows of A prime, so in order for this guy at the left-hand side to be stationary, this guy here at the right-hand side that still contains the unit root must disappear. And when does it disappear? Well, that only occurs if the matrix in front of it is 0. So therefore, from this analysis, we conclude that in order to have co-integration, we need to have that this matrix indicated in the box over here is a 0 matrix. So the guy in front of the partial sum. Now let's have a look at an illustrative example to see how we can use this condition to obtain a co-integrating vector from an example. And throughout these videos, I will work with this example from the graphs that I've shown before. So the right panel of the plots that I showed you earlier. We have this example where the second series in differences is just equal to an IID error. The first series in differences contains, let's say, the links between both series. Now, how can we obtain our co-integrating vector from this condition that we derived on the previous slide? Well, start from the VMA representation of the series in differences, which is our lag polynomial psi L times the error term, the IID error. What is our lag polynomial psi L in this case? Well, the first series in differences is nothing more than the difference of the first error component, so 1 minus the lag operator times the first error, plus beta times the second error. And for the second time series, well, its difference is just immediately equal to the second error term. So that's how I obtain psi L for this example above. Now in the condition, psi for L equal to 1 is popping up. So we need to plug in the value L equal to 1 over here to arrive at psi 1. And that is this guy here. Now let us introduce then the co-integrating vector A prime, which is the first and only row here in our matrix A prime. And this vector A prime needs to satisfy here this 0 restriction from the box. Now, for which vector is this true? Well, this is true for the vector 1 minus beta, because you can see this immediately from, let's say, the second column by expanding this matrix product. All right, so in the next video, we will have a look at various ways to represent our co-integration relations.